So we have discussed so far that reactions need to take some routes to be able to occur and produce the products. And the routes that we are going to talk about is actually called the reaction mechanism. So in principle, when we see a reaction, what we immediately see from textbook or from other sources is actually a total reaction. Take a look at this reaction so we can understand it better. This is a decomposition reaction of N2O5 gas to form two different gases, which are NO2 and oxygen. What you are seeing here is the total reaction. This is what we observe experimentally, that if we have 2 moles of N2O5, we will then get 4 moles of NO2 and 1 mole of oxygen gas. Now, I have mentioned before in our meeting that you cannot say that R is equal to K and then take the reactant and then take the coefficient of the reactant as the order. This is not the right way to go. The order should be determined, again, based on experiments. However, we can take a look at the actual steps of this reaction that we call the elementary steps or the elementary reactions, meaning that the actual collision that occurs at the molecular level. For this particular reaction, the proposed mechanism is as follows. The first reaction would be that one molecule of N2O5 will first dissociate into NO2 and NO3. Second reaction is that 2 molecules of NO2 and NO3, so each one, will then result in NO2 plus NO plus oxygen. And finally, there is a final reaction, which is the third one. Then this one is NO plus NO3 forming 2NO2. So this is what actually happens at the molecular level. In this case, one molecule of N2O5 will dissociate into NO2 and NO3. In the next step, 2 different molecules will collide together. And if they have a correct orientation and they have energy that overcomes the EA, it can produce NO2, NO, and oxygen. And finally, the NO will react with NO3, forming 2NO2. Now, based on the number of reactants, we can call the first reaction a unimolecular reaction. Unimolecular reaction. Because you have one reactant. So that would be the first reaction, the example. We can also have a bimolecular reaction. That means we have 2 reactants. And we can see this in the step 2 and also step 3 where we have 2 molecules of reactants. We can also have, say, termolecular reaction, but we don't have the example here. Termolecular reaction is when we have 3 reactants, but we don't have the example here. And as you can guess by now that it is very hard for us to get a termolecular reactions because don't forget that the reactions is based on collisions. You can imagine cars being crashed with one another. The possibility of 3 cars colliding head to head, so with a correct orientation, will be way lower in comparison to only 2 cars and only 1 car colliding on its own. So in this case, more often than not, in the elementary steps, we will get unimolecular reaction or bimolecular reaction. Just like this one, this is uni, and these 2 are bimolecular reactions. Now, if we sum up the elementary steps, we should get the total reaction that we have in the beginning. So here we see that we have to multiply the first equation by 2. So then again we get 2N2O5, and after that on the right side we will get 4NO2 and 1 oxygen. And you can see that there are some substances that we will cancel out. Let me cancel it out in red so we can all see it quickly. It's going to be 2NO3, and the other one would be the NO. So immediately you realize there are some substances that do not present in the reactant side nor at the product side. And we call this the intermediates. So per definition, intermediates are substances that we form during the reaction, but also those very same substances will be consumed in the next steps. So in this case, we have two intermediates, which is the NO3 and also the NO. As you can see that NO3 and NO, both of these guys, they do not present at the reactant side, neither at the product side. But during the reactions, they are formed and they're consumed again at different steps, and therefore we do not have them at the final or at the total reaction, and this is what we call the intermediates. So the things that we cancel out will be the intermediates. Now, although it's not okay to take coefficient as the order of reaction for total reaction, it is doable for elementary steps. So say for the first reaction, the R1, or the rate of first reaction, is equal to K N2O5 power to the second because it has 2 as its coefficient. For R2, it's going to be K multiplied by concentration of NO2 and NO3 each power to the first because that is their coefficients. While for R3, or the rate of the third elementary step, we will get K equal to NO multiplied by NO3. Because now we are talking about reactions and collisions at the molecular level, it is okay to take the coefficient as the order. And this is again only okay or only doable if you are looking at the elementary steps, but never okay for the total reaction. And from different steps like this, we can determine based on experiments again, and we rechecked it with the reaction mechanism that we are proposing. We have something that we call the rate determining step. So say again that we have 3 steps of reactions, just like what we have in the previous reaction. The rate determining step is the one with the lowest rate. And more importantly, the rate determining step will actually dictate the rate law for all of the reactions or the total reaction. So in this case, let's come back again to our example. If we say that the first reaction is the rate determining step, or RDS, then the R of the reaction itself, that I will write as R like that, is going to be equal with the R1. So K will be N2O5 power to the second. In this case, it is a coincidence that the order here is the same with the coefficient at the total reaction. However, as I mentioned, for total reaction, you cannot immediately take the coefficient as the order, but you can do it for elementary reactions as such. And the elementary reactions, that is the RDS, or rate determining step, or the lowest rate one, the R of its step will determine the entire R. And we can recheck whether this is checked out with the experiments. Now, if we have proposed a mechanism and we have also proposed the rate determining step, but then it is against the experiments, then that means our mechanism is wrong. So the kinetics is a very experimentally based chapter. If the mechanism that we suggested does not concur with the experiments, then the experiment would be the correct one. We have to propose a new mechanism that would match the experiment results.